We have a system consisting of two tanks. And this is a mixture problem. Now, we have two tanks, and instead of the kind of examples we had before, where we could have one tank flowing into another, and then maybe solution flowing out of that tank even, we have the possibility that solution flows in each direction between the tanks, so that some of the fluid from this tank can flow this way, some can flow this way. Also that there's a source for each tank other than the solution from the other tank. So each tank has an input and an output pipe, okay, and a pipe that extends to the other tank. And we pump water at we pump solution at a certain rate from each, well, through each pipe. Okay, so that this tank, what we'll call the first tank, will have at any instant some amount of, and I'll say salt, because typically we phrase this in terms of saline solution, but it could be any solute. So you can substitute the word solute for salt. Salt is shorter, so I'm going to say salt instead of solute, and we can identify with salt. It's less abstract. Okay. Now I'll note that this Q1 and Q2, which stands for the quantity of salt in the first tank and the quantity of salt in the second tank, are functions of T. As things flow around this system, we understand that the amount of salt in each tank is going to vary. Okay. Now, we have solution flowing into the first tank with concentration A at rate R1, into the second with concentration B flowing in at rate R2. We have solution flowing at rate R12 from tank 1 to tank 2, and at rate R21 from tank 2 to tank 1, and solution flowing out at rate R1 from tank 1 and R2 from tank 2. Now, the fact that R1 is, well, that we have R1 both from here to here, well, both here and here, and R2 both here and here, means that the amount of stuff in each tank is going to remain constant. Well, that doesn't necessarily mean that. If the tank's originally full, it means that. Okay, so this could mean that R12 and R21 also have to be equal to one another. But there are many variations possible on this situation, and none of those, there are no conditions on the situation other than that tank 1 has some fixed volume V1, tank 2 volume V2. We don't assume either tank is necessarily full or necessarily empty or anything like that. We don't, and we, in general, could have a different outflow rate here than we have an inflow rate here, different outflow here than inflow here. There are all kinds of conditions on the flows between the tanks and into and out of each tank. So I've given you a simplified set of flow rates. I could have R1 in, R1 out, R2 in, R2 out, and then I could still have R21 and R12. So most of the examples in the book are actually somewhat even simplified than this. Maybe all the rates are equal. Okay, now what we want to know is, with all this solution flowing around, what is it that influences Q1? Well, certainly one thing that's going to tend to influence Q1 is how much stuff is flowing in, and another thing is how much stuff is flowing out. And also how much is flowing in from whatever your source is here, and how much is flowing in from the second tank, because you got stuff flowing in from the second tank. And for the second tank, how much is flowing in from its source, how much is flowing out in its exhaust, if you wish, and how much is flowing in from the first tank. So let's think about how Q1 is being affected. Well, at any instant, Q1 is changing at some rate that depends on all these parameters and also on Q2 and V2. And let's see how that is. So what is it that influences the rate at which the amount of salt in tank Q2 is changing at any given instant? Well, certainly the rate at which salt flows in at concentration A. That would be this pipe. And what's the rate at which salt flows in? You multiply the concentration A by the rate at which the solution is flowing in, okay? So that would be R1A. Now, we talked some about, we have these symbols and we have our common sense and our numerical sense. So it just is a numerical example. If R1 is 15 gallons per minute and the concentration is 10%, then we're going to have 10% of that 15 gallons, meaning we're going to take our 10%, which is 0.1, and multiply it by that 15 gallons per minute rate. And this product is going to give us the rate at which salt is flowing into the tank here. And that's, of course, going to be 1.5 gallons per minute if A is 10% or 0.10, and R1 is 15 gallons per minute. So, okay, so we need to connect that, and that's not always easy to connect, so you want to think about that. The rate at which salt flows in, flows out, it's going to be influenced here, flowing out to the ocean, let's say. You know, this stuff flows out, it goes eventually to the ocean. Which is a good place for a salt solution to end up, okay? R1 is the rate at which solution is flowing out here. What's the concentration? It's not A. What's the concentration of the fluid that flows out here? Well, it's Q1 over V1, isn't it? Okay, amount of salt divided by volume. Now we're going to assume that V1 is the volume of the container. Right now, let's assume that the volume of the, well, no, let's not make that assumption. I wasn't real specific on that. Okay, I'm going to say volume V1 of T and make volume V2 a function of T. Because the tank might initially be empty. Or it might be partially full. Or it might have been full, but it's flowing out faster, it's flowing in. So it's emptying. So V1 and V2 will generally be functions of T. Often they'll be constant. So one way or the other, at time T, the concentration is Q1 over V1. Q1 meaning Q1 of T over V1 of T. Okay, that's the concentration. So at what rate is salt flowing out? Because that's, or at what rate is salt, is what rate is salt flowing out, which is going to contribute to dQ1 dt, right? And that's going to be R1, the rate at which solution is flowing out, times concentration Q1 over V1. Okay, and then very similarly, the rate at which salt flows in from tank 2 is what? Well, it flows in with what concentration? What concentration is flowing in from tank 2? Well, it's going to be Q2 over V2. Okay, so that's the concentration of what comes in through this pipe. And of course the rate is R21, so the rate at which solution flows in here is R21 times Q2 over V2. And the rate at which salt flows out out to tank 2 is what? Concentration Q1 over V1 is what, that's the concentration of what flows. It's flowing at rate R12. So the rate at which it flows out is R12 times Q1 over V1, the rate at which salt flows out. Now we put all that together and we get a straightforward equation that says that dQ1 dt is, and people had an easy time writing the equation, reasonably easy time. Most people got it. Some people need a little bit of a push, but got it okay. And saw it, and everybody was able to write this one after having maybe had a little guidance in writing this one. So, okay, well, you have R1A flowing in, and you have R21 times Q2 over V2 flowing in. So here's what flows in, and that's all positive. And you have R1 times Q1 over V1 flowing out, and R12 times Q1 over V1 flowing out. And we simplify this expression, and we get what I have here. I don't have to read it to you. You understand how it simplifies. Okay? And then we can do the same thing for Q2, and everybody was able to write down what looked like a good equation. I didn't check all the subscripts and everything. Better for the class to check my subscripts, because that's where I tend to screw things up. I'm not as good as I should be at keeping up, at the bookkeeping aspect of all this. Okay, well, so the dQ2 dt is R2B, and we can see there's R2, there's B flowing in, that's positive. And R12 at concentration Q1 over V1, okay, that works. And then flowing out, we have R2 at concentration Q2 over V2, and R21 at concentration Q2 over V2. And that's what we have here. We subtract the sum of those. So that we can write this equation, Q prime, well, I don't have to read it to you. I'm writing it, though, using Q prime. And I'm taking the Q1, all the coefficients of Q1 here, and the coefficients of Q2 here, and leaving my R1A out here because that doesn't involve Q1 or Q2. And here, I do the same thing, multiple of Q1 here, multiple of Q2 here, and the R2B. So it's a nice organized form, and we begin to see this as an equation in the derivatives of Q1 and Q2, in terms of Q1 and Q2, and some constant input, or some part of the input that doesn't depend on Q1 or Q2. And this is going to become kind of, you know, a differential equation, but a system of equations. And here's going to be your non-homogeneous part. All this could come over on this side and so forth. It really won't, because you'll see what we do. But you see how this system of differential equations comes about, and how it accounts for all the interplay within the systems. And you can imagine if I had a system with a bunch more tanks with a bunch more pipes, how you could still write these equations if you know all the pumping rates.